Option 2, to calculate the expected frequency, is calculate each allele individually using the Hardy-Weinberg equation, which is p squared plus 2pq plus q squared equals 1, where p and q are the frequencies of the two alleles. In this case, I'll use p to represent the frequency of A and q to represent the frequency of C. So therefore, we must calculate the frequency of allele A and the frequency of allele C. So in order to calculate the frequency, we would take the total instances of that allele divided by the total amount of alleles. So since each of these are diploid organisms, diploid meaning 2 copies of each gene, that means we'll have, while we have 100 diploid organisms, we'll have an allele population of 200. So let's look at the probability of the A allele, where we look at the homozygote for A, and since there's 81 instances of that, we would multiply 81 by 2, because for every A homozygote, there's 2 A alleles. And then when we look at the heterozygote, and we would see there's 13 instances of that, but that only yields 13 additional A alleles. So then we would calculate that here, 81 plus 13, divided by 200, and that would give us this probability here, 0.875. Alternatively, we'll do the same thing for the C, in which case there's 2 C's for the homozygote, meaning for the 6 observed frequencies here, we would have to multiply that by 2 since there would be 2 alleles here. And then for AC, we would just add that 1 because there's only 1 instance of the C allele for the heterozygote. So we'll plug that in here and we'll get this value as well. So these two are probabilities. And we'll take these probabilities and we'll look back to the Hardy-Weinberg equation, and using the expected using the discovered allele frequencies, we can calculate the expected frequencies of the genotype, where the frequency of AA is equal to p squared, and the frequency of AC is equal to 2 times the frequency of p times the frequency of q, and CC is equal to q, which is the frequency of C, squared. So we'll take those values again. AA would equal p squared, so 8.75 squared, and that'll give us a frequency of 0.7656, and that here's a percentage for that, and we'll just carry that out each time. And here are the percentages of it. And I calculated the total percentage here because it should ideally equal 100. Oops, I think I have a rounding error somewhere. But these are just percentages. So we would need to multiply the percentage by the total number of individuals in the population. So since there's 100, since the total is 100 in this case, it does make it much easier. I could just erase the percentage points, and here we have the expected frequencies of each. And then from there, you could take this data, fill it in the table, and calculate the rest.